induced voltages and inductance. So this is the chapter where we will see that magnetic field can create electricity. So that's why I call induced voltages and inductance. We will see how. These are the contents of this chapter. We will cover 1 to 3 now. This will come after the midterm 3. Okay, so in midterm 3, from chapter 20, only the first 3 sections, and the rest of the section will be postponed to the final exam. So we will finish it in this lecture. Okay, then next class, Wednesday, we will do review for Sunday exam. Yeah, the next Wednesday. Why? No, I will have attendance. Right, now, so a little bit of history. In 1819, we told this before, this one, Ørsted, he discovered, from electric current, we will have magnetic field. So when you bring a compass near a current carrying wire, it deflected. So, please put your screen down. Pay attention here, please. Down, please, your screen's down. Your screen is here, big screen. This is the first evidence of a link between electricity and magnetism. Then, 1831, Faraday and Henry independently, they showed a changing magnetic field could induce an electric current in a circuit. So then it led to his law, Faraday's law. By changing the magnetic field, you can get electricity. Inducing an electric current, there must be it act like a source of EMF. This induced electric current is coming from the change in magnetic field. So we will see how it is discovered and how he made this Faraday's law by doing several experiments. So this is Michael Faraday. He was born 1791, died 1867. He's a great experimental scientist. Invented the electric motor. We saw that in the last chapter, how the electric motor works. So send a current through a coil, keep it between a magnet, and it starts rotating. That's an electric motor. Also, he invented generator. This is the opposite. So electric motor is, from electricity, we get mechanical energy. In a generator, we convert the mechanical energy to electricity. We will see how it is done. He also invented transformers. Transformers are devices that change the voltage. So an AC voltage of say 220 can be transformed to 110 volt. This is transforming from one value to another value. These are called transformers. He discovered electromagnetic induction, and also he discovered the laws of electrolysis. Maybe in chemistry, probably learned this electrolysis. Right, this is the experiment it made to the discovery of his law. What we have here is a coil which is connected to a battery through a switch, and there is another coil called the secondary coil. It is not connected to the battery, only the primary coil on the left is connected to the battery. However, he observed, whenever he closed the switch, so there's a current that flows through this coil, the primary coil. He observed from the voltmeter or the current meter there is a current through the secondary coil as well. this battery is no way connected to the secondary coil. It is separate because this is the iron core, that traps the magnetic field, that is, make the effect more magnified. But there is no current that can flow from this wire through the core to the other one because the wires are insulated. So it is like, there is some, all of a sudden there is an induced EMF in this coil, so it sends a current through the secondary coil as well. We can repeat this Faraday's experiment virtually. So I'm going to click on this link and I will explain what he observed. Right, so we see this one battery is connected to this coil, the left hand, let's call it primary. And there is another coil, let's say call it the secondary. It is not connected to the battery, but let me also take the bulb out and put a meter. So watch. Now currently the battery is connected. There's no switch, but what I will do, I'll bring it to 0. That means I'm switching off, right? So now it is open, like open circuit. So the battery is not 0 volt, so nothing going to happen. No current in the primary, also no current in the secondary. Now I'm going to bring it quickly by clicking here to 10 volt. It is like closing the switch. Then watch this voltage here. It is not connected, okay, but when I close the circuit, I mean I bring the voltage here to 10 volt, watch the needle, okay. Did you note that? It flipped to the left. When I close the switch, for an instant, there was a current through the secondary coil as well. Now let me close the switch, I mean open the switch, bring it to this and watch again. It went to the deflected the other side. So when I close the switch, it deflected to the left. When I open the switch, it's deflected to the right. Now, why do you think this happened? Now, let me close the switch again. See, there is a magnetic flux now. Before, there was no magnetic field through the secondary coil, and suddenly when I close the switch, there is a magnetic field through the secondary coil. So when I open the switch, the reverse happened. There is a magnetic field. When I open the switch, the magnetic field vanishes. So he concluded, right, from this experiment, he's a very good experimentalist, so he's very sharp observation. So he concluded whenever the magnetic field is changed through the coil, there is an induced voltage or induced EMF. Excuse me, come to the front, please. Stand up here, come to the front. Sit here. So this led to the Faraday's law. So he figured out changing magnetic field will create or induce voltages in the secondary coil. That's why we observe the current. There is no battery in the secondary coil, right? So current is not coming from the battery. There is an induction of voltage in the secondary coil. So this is a big discovery. So what he observed was when the switch is closed, the ammeter reads the current and then return to 0 very quickly. It is not continuous current. When the switch is open, again the ammeter reads the current in the opposite direction, then returns to 0. But when there is a steady current, okay, because when you close the switch of the primary circuit, there is a magnetic field through the secondary coil, but it is the same value. It is not changing. So that's why the induction is observed only when you close for momentarily and when you open, because there is also a change. When you open the switch also, from a lot of magnetic field through the coil, then there is 0 magnetic field. Whenever there is a change, there is an induced current. Otherwise, no induced current. only when there is a change. Okay, Faraday's conclusion: an electric current is produced by changing magnetic field. The secondary circuit acts as if a source of EMF is connected to it for a short time, when only there is a change happening. When there is no change, it is not a source of EMF. So it is customary to say an induced EMF is produced in the secondary circuit by changing the magnetic field. Whenever there is a change in the magnetic field, we are going to get an induced EMF. This EMF is actually induced by a change in the quantity called magnetic flux, not just the magnetic field. So the concept of flux is not the first time you introduce. You already know about electric flux, right? You learn something called electric flux. So it's a similar thing. The magnetic flux is proportional to the strength of the magnetic field, like the electric flux is proportional to the strength of the electric field. And the area of the loop through which the magnetic field is being linked. So you can talk about an electric field through a certain area. So that flux through that certain area is proportional to the strength of the magnetic field and the area of the loop. So we can introduce that similar to what we did with the electric flux. So imagine you have a loop like this, so it defines a certain area. So that's what you see, this loop. And the perpendicular to the loop will be the direction of that area. So the area itself has a direction. So let me call it, this is the vector area. So that is perpendicular to the plane, okay? So the area has a direction perpendicular to the plane. And let's say this green arrow is the magnetic field direction. So we say that the flux is equal to the component perpendicular to the plane. In other words, it's actually the component of the magnetic field parallel to the area. So, although it is a bit confusing here, it's perpendicular to the plane, but it is going to be the parallel to the area vector. The angle between these two vector, theta, say that angle is theta, then the perpendicular component will be b cosine theta. Actually, it's the parallel component to the area A will be b cosine theta. So that's how we define the magnetic flux. The same symbol, if you remember, for electric flux also you use this Greek symbol phi, but with the subscript E. Now since this is magnetic flux, it will be with the subscript B. The unit will be Tesla for the magnetic field, and for the area, meter squared. So it is Tesla meter squared, but we give a single name for that. We call Tesla meter squared as Weber, okay, Weber, WB, 2 letters, capital W and a small b. Right. So now we define the flux. The reason for defining the flux, because Faraday initially thought that, okay, the magnetic field change will give rise to the induced EMF, but it is actually change in the flux, not just the magnetic field, also the area concerned. Okay, so here again taking you through the magnetic flux. So here we have the ring placed with the area of the ring will be perpendicular to the plane, and this is the magnetic field. What is the angle between B and A? When you keep it like this, it will be 0. No. The direction perpendicular, because the area is this. The vector area is, I'm asking you the angle between the vector A, which is the area vector, and the magnetic field vector. So they are in the same direction. That means angle is 0. So the component of the magnetic field along the vector A is everything. Theta equal to 0 means cosine theta will be cosine 0, right? Cosine 0 is 1. Don't confuse with the sine and cosine, okay? Sine 0 is 0, sine 90 is 1, but cosine 0 is 1, cosine 90 is 0. Okay. Right. Now, when that happens, the flux is maximum. So you can visualize the flux as the number of magnetic field line that is going through this area, right? So suppose I put it like this. Is there anything going through? Or the line will be grazing. It will not be going inside that. So angle is, because this will be the area direction, this will be the magnetic field direction, the angle is 90. Theta equal to 90. Cosine 90 is 0. Okay, again, sine cosine, don't confuse them, mix them. Cosine 0 is 1 and cosine 90 is 0. So it all work out well for us, right? The flux is equal to B cosine theta, the component of the magnetic field along the vector A direction, multiplied by the area. So here, whenever theta is equal to 90, that means it is like this. Theta equal to 0, it is like this. That will be confusing, but I hope you understand. Of course, perpendicular to the plane, but it is parallel to the direction of the area, because direction of the area is perpendicular to the plane. Yeah, but the thing is, it doesn't matter. More than 90 is corresponding to negative angle, right? I mean, you can kind of think of it like that. So this is 0, right? So when it is like this, it's positive 90. When it like this is negative 90. So you can think of it again as 90, because cosine minus 90 and cosine plus 90, cosine 90, yeah, it will be negative sine, okay, minus 1 and plus 1. Cosine 0 is 1. Cosine 90 is plus 1. No, cosine 90 is plus 1. Cosine minus 90 is minus 1. Yeah. So it's just a switching of the direction. So the flux can be visualized with respect to the magnetic field line, that what we saw in the previous picture. So you can say the magnetic flux is proportional to the number of lines passing through the loop. More number of lines, when it is like this, everything is passing through, right? When you go like this, the number of line will be decreasing as you tilt. As you come like this, it will be 0 number of line. So, right, now I'm going to continue with this flux thing, okay? But we just first saw, right, when the magnetic field is changing, we are going to have the induced EMF. But we then said it's actually the flux, not just the magnetic field. So to explain that, let me open this simulation, again in the same virtual lab. Right, so this is a magnet, right? Magnet has magnetic field. Let me show the field line. And I put a voltmeter also. Now there is lots of magnetic field line going through this loop. Is there a current? Is there an induced? Is it acting like a battery? No. Why? The flux is not changing. Magnetic field is the same thing. But if I move it, would you expect it to change? Of course, it's going to have more magnetic flux. It's not just the strength of the magnetic field, it is also depend on the area. So now let me move it inside. Say the bulb is come and the needle is, okay, let me bring it back. The needle is going to the left and the bulb is coming on. So it is becoming like a battery. So it is momentarily, when it is changing, it has an induced EMF. What do you think will happen if I move to the right? The needle will be in the opposite direction. When you close, it is in this direction, move in this direction. So this is the number of loop is 4. Let me introduce another loop and I'll slowly bring it up. Do you think the effect will be less or more now? Here it has only 2 loops. It will be less because each loop is going to contribute. Here you have 4 of them. Here only we have 2 of them. So the effect will be little less. Okay, if I bring the same velocity, assuming. So let me do it here with the same velocity. So you can see the effect is more. It depends on the number of loops, as well as the, I wish I can show with this big loop, but I have the same size here. So it will depend on the area of the loop as well. There's no way to shrink the area. Anyway, right. So this is to demonstrate the whole thing. So Faraday, did so many experiments. We took numbers and so on. Then he finally come up with this equation, which is called the Faraday's law. So what is Faraday's law? Okay, we are not there yet. So let me repeat this again. A current is there as long as there is a relative motion between the magnet and the loop, right? When it comes closer, you are changing the magnetic flux, so there will be an induced EMF. It doesn't matter which is moving. You can keep the magnet in the same place, but move the coil. It will also have the same effect. So it's the relative motion which changes the magnetic flux through the coil. The same experimental results are found whether the loop moves or the magnet moves. This current is called the induced current because it is produced by the induced EMF because of the change in the magnetic flux through the coil. So the instantaneous EMF induced in a circuit is equal to, now this is the law. Let me just bring your attention to the equation. So we use the symbol E for the EMF, which is the induced EMF. So Faraday said it is proportional to the rate of change of the flux through the coil, the rate of change of flux, how fast the flux is changing. It's not just the magnetic field, not just the area, it's both, the flux. Also, it depends on the number of loops. More number of loops, the effect will be more. Will be increased linearly with the number of loops. So this is the Faraday's law. The induced EMF is proportional to the number of loops and also proportional to the rate of change of flux. So delta phi mean phi final minus phi initial. The change in a certain amount of time, t final minus t initial. That gives the rate of change of the flux, how fast the flux is changing with time. So if we know the equation for the flux is this. So how the flux is changing, it can be due to, if I expand it, because B changes, the flux can change. Because A is changing, the flux can change. You can also change it by changing the angle. So there are 3 ways by which we can have a change in the flux. And the sign negative in the equation for the Faraday's law, it tells you the direction of the induced EMF. It is more, the direction of the EMF is given by what we call the Lenz's law. Of course, already there in the Faraday's law in this form, the negative sign tells you the EMF will be in the opposite direction to the change. That's what this negative sign indicate in Faraday's law. But it is easier to use this descriptive statement, which is called the Lenz law, to find the direction. So we can just simply ignore this negative sign. We will only find the magnitude. So the magnitude comes from the Faraday's law, and we will use this Lenz law to get the direction. The current caused by the induced EMF travel in the direction that creates a magnetic field with flux opposing the change in the original flux through the circuit. So probably it is best described with an example. We have in the next slide an example. So if you can do that exercise, you will know how to apply the Lenz law. So let me go to the next slide. Here it is. We have a conducting loop, a loop made of a conducting material. So, and we keep this in a magnetic field. So ignore this. I'm going to hide it, these things. So what we have is a conducting loop, and we apply a magnetic field. So the conducting loop is perpendicular to this magnetic field, and B is straight up. And it's a uniform magnetic field. Okay, it's a uniform magnetic field. That means everywhere it is the same magnetic field, same length. But we change the magnetic field simultaneously everywhere. So we reduce this magnetic field. Let's say initially it is 100 Tesla. And after 1 second, say it becomes 75 Tesla. Another 1 second becomes 50 Tesla. So we keep decreasing this magnetic field. The direction is up, yeah, and we decrease in the magnitude of the magnetic field in this manner. So we have a change in magnetic flux through this area. The magnetic flux is changing. What will happen now? According to Faraday's law, you will have a induced EMF, therefore an induced current through this coil. No battery, nothing. Just because the magnetic field is coming down, so the flux is changing, there will be a current in this coil. But we can use the Faraday's law and get the how much current it is. But what about the direction? Is it going to flow this way? That means looking from above counterclockwise, or it is going to flow the other way, looking from above clockwise. Clockwise or counterclockwise? Counterclockwise, why? What do you mean by right-hand rule? Why? I mean, I'm asking you why. Magnetic field is up? No, magnetic field is not from the current. It is, I apply the magnetic field. I apply a magnetic field, and the magnetic field size is, I decrease the magnetic field. That means I have a change in the flux. The Lenz law says the induced current will flow in such a direction, so it will oppose the change in the original flux. The original flux is the applied magnetic field give a certain flux. So what is happened in the original flux? 100 Tesla become 75 Tesla. How much has decreased? Say 25 Tesla decrease. In which direction was that? No, I mean, the magnetic field is up, right? It is from 100 Tesla up, it becomes 75 Tesla up, still up. So you are changing it by 25 Tesla in the upward direction. So he doesn't want it, doesn't want change. He will oppose the change. Oppose the change means you have to provide 25 Tesla in the upward direction. Okay. Yeah. So the induced field, this guy has to induce a field So you will get a 25 Tesla in the same direction because it has decreased, right? So I don't want it to decrease. I have to provide a magnetic field in the same direction. So I compensate the loss. I don't want the change to happen. Right. Now the induced field is needed 25 Tesla. I have to provide that. What direction should the induced current flow to get that induced field? Counterclockwise. Right. Right hand rule is apply the right hand rule. So you get it need to be moving counterclockwise. Right. If I change the problem, let me say the applied original field is down. Original field, okay, original. External field is down. And I increase the field. I make it 100 to 125. What direction will the current flow? Why? No. Why? Yeah. Explain it, okay. Let's say this 100, let's use number. Then it become 125 in the same direction. Yeah, no. What I'm asking about the induced field. Let me use another color. It is 100, 100 become 125. So it is increased, right? So how should the current flow to stop this change? 100 become 125. So I have to give a field in the opposite direction. I don't want it to increase. So the induced field must be up 25, right? Induced field must be, because 100 external field became 125 external field. I don't want change. So how can I oppose this change? The change is what? 25 down. So I will add 25 up. So it will cancel the change. So the induced field must be up. So the current should flow counterclockwise. Okay? Current should flow. We can have two more examples, but yeah. Why the? Negative? Don't talk negative, positive. Just tell me the direction of the induced field. If down and increasing, induced field must be up. If down and increasing, the original field is down and increasing, how do I oppose this change? I should have an induced field up, right? Okay, let me give one more example so that I will. Right. Now let me say up. Okay. Up and decreasing. This 100, right? And becomes 75. No, that is what I said before. Up and increase 125. Okay. So up and increasing. What should I do? Say I am the loop. I should try to stop the change, right? So induced magnetic field will be down. Induced magnetic field will be down. How should I send the current? So to get it down, I have to send it clockwise. Okay. So actually you can think of 4 scenarios, right? 4 combinations. Up and increasing, up and decreasing, down and increasing, and down and decreasing. So for all these 4 cases, you should be able to answer it correctly. So now we can do this question. Applying the Faraday's law also to get the direction, Lenz's law. So we have a loop, something like this, and we send we don't send anything. We keep it in a magnetic field. The magnetic field direction is this. Do you understand the direction? What do you mean by this? Cross means into the board, perpendicular to the loop. And it is decreasing at this rate, Tesla per second. That means this is the delta B. The magnetic field is decreasing. Delta B over delta T is 11. Not delta phi. Delta B over delta T is 11. What do you think will happen? There is a magnetic field, and the magnetic field is changing. That means the flux is changing. So according to Faraday's law, the magnitude of the EMF will be equal to N delta phi over delta T. I took the magnitude. Okay, I will get the direction from Lenz's law. So I just want the magnitude. Only one loop. So N is equal to 1. Phi is equal to BA cosine theta divided by delta T. Is A changing? No. It's the same loop. A is not changing. Is theta changing? What is theta, first of all? Angle between what and what? Angle between two things. Between the plane and what? The perpendicular to the plane. So this is the perpendicular to the plane, okay, and the magnetic field. They are in the same direction. Magnetic field is perpendicular anyway, and the plane perpendicular to the plane is perpendicular. So the angle is equal to 0. Cosine 0 is 1. So I can forget about this. And A is not changing. So I can take it out. Now I can substitute. A is equal to 20 by 20. That means in meters it will be 0.2 square. And dB by dt is given in the question 11. So you will find the EMF. But he wants the current. So this is having an EMF of this much. Divide by the resistance will give you the current. So you can get the value, right, fine. We can get the induced EMF, also we can get the induced current. But I have another question. What is the direction of this induced current? Clockwise or counterclockwise? Clockwise. Why? No, yeah, explaining is a bit not so correct, yeah. What is going inward? Yeah. The magnetic field is going inside. You don't look at that magnetic field, no. That is my magnetic field, not the magnetic field from the, it's not the induced magnetic field. So you are jumping to looking at this one. It has, you have to first find out what is the direction of the induced magnetic field. The current will flow. Okay, this is the ring, right? And there's a magnetic field. What is happening to this magnetic field? How is it changing? Increasing or decreasing? Because it says in the questions decreasing. So you just ignore everything and you're looking at the original magnetic field. You don't look at the original magnetic field, you look at the induced magnetic field. The induced magnetic field is the one that comes from the current, right? The induced current. So tell me what should be the direction of the induced magnetic field. The original magnetic field is in, the outside external magnetic field is in, and it is decreasing. So I have to stop that change. Down and increasing. What should be the induced magnetic field? It should be opposite, right? Yeah. So the induced magnetic field must be opposite. Okay, right. So the increased magnetic field must be opposite. This is in and decreasing. So it should be out. Induced magnetic field must be out. If it is out, which direction should it flow? I'm sorry, not increasing, decreasing. It is decreasing. So the in is decreasing. So I should provide a induced magnetic field. It must be also in. Okay. Outside magnetic field is in and decreasing. How can I challenge it, cancel it? I should provide an induced magnetic field or in. So the change is cancelled. Okay. Are you all okay with me? No. No. Wait. Okay. We have original magnetic field and it is decreasing. I don't like it. How can I stop this change? I should provide a magnetic field also in, so I will cancel the change. No, not about increasing, decreasing. I should see. Imagine like this. So this is 100 before. Say it is 100, and it become 75. How much change? 25 Tesla less now, right? I should provide that 25 Tesla in, so it is the same as before. I mean, I will provide, some magnetic field to cancel the change. So that means the induced magnetic field must be in. What is increasing, decreasing, changing is the external magnetic field. Don't bring that to the induced magnetic field. Okay? Right. So if we want it to be in, what should be the direction? Clockwise. Right? If you want the magnetic field to be in, induced magnetic field to in, I should send a current clockwise. So through the 10 ohm resistor, it will be going B to A. Yeah. Yeah. If the magnetic field is in and increasing, then induced magnetic field should be out. Yeah. Because I want to oppose the change. That is the Lenz law, application of the Lenz law. Okay. So this has been done here. So the direction, the induced current should be flow clockwise to oppose the change. When it is go clockwise, it will provide a magnetic field also into the board, so cancelling the change. Right. So we have an application of this Faraday's law in a safety device in homes, what is called the ground fault interrupter. So when you have in your working at home and you're using some electric shock, okay, because if the current comes to the body of the instrument, that means some of the current is getting out, right? So suppose in the home circuit you have the wire 1 which is bringing the current. Let's say this is coming in from outside and it goes through this device called GFI and it will supply to all your appliances and come back wire 2. Coming in, going out. These two wires are very close together, and if there is no leak anywhere in the apparatus, the current I that comes in will be equal to the current that goes out. Current 1 will have a magnetic field around it. Current 2 will also have magnetic field, but they will be in the opposite direction. So the magnetic field outside will be 0 because of the two wires cancelling the magnetic field. So we have something called a sensing coil. It will see there is no magnetic flux through it, 0 magnetic flux, no problem. But if there is a leak, excuse me please, if there's a leak in the apparatus, that means the current that goes in will be different from the current that comes out. So the magnetic flux now not going to cancel each other. There will be suddenly from zero flux, you will have a flux through the changed flux through the sensing coil. What happened? Faraday law jumps in. Whenever there's a change in the flux, there will be an induced current. So that will be detected by the circuit and it will break the circuit. There will be a circuit breaker, so it's a safety mechanism. So you're saved, there will be no shock. Immediately the circuit breaker will, yeah. So this is called a GFI. Another application, electric guitar. You know, guitar, the musical instrument, the sound is normal sound, natural sound. So, but electric guitar, what they do, this when you vibrate the string, we will have it closer to some magnet, and through the magnet we have this coil. So the magnetic field will be cut by this string. So that will generate a change in the flux, and there will be an electric current that runs through this pickup coil, called the pickup coil. And that electric signal will correspond to this vibration. The sound vibration is now translated into an electric signal, right? So when you have an electric signal, it can be amplified. When you have an electric signal, amplified means increase the size. Suppose if the signal is like this, electric signal, we can use something like amplifier. It will be like this now, magnified. So then it go to the speaker, then go back to signal, become back to vibration. So you'll have a loud sound. If this electric guitar, has a louder sound than the normal guitar because of this. This is another application. Premature baby, when they are born, they keep it under observation. So there is this coil wrapped around it. If the baby is breathing, there will be a certain current, through the Faraday coil, pickup coil, we'll have electric signal. So everything is fine. But the breathing stops, there's a change in the flux. It will be detected by the electronics, then it will be alarm the nurses. Right. Then we have this, the last topic, because the section 3 now, motional EMF. What we have here is a conductor, straight conductor. Okay. It is kept in a magnetic field. And you see again, it's a uniform magnetic field. That means it is everywhere the same value, but it can change with time. When it changes, all of them change together. But here, no, we don't change the magnetic field. It's the same everywhere, uniform magnetic field. And we got it's not by changing the field, by motion we will get an EMF. Let me explain that. Conductor has free electrons, right? Conductor has free electron. So this rod is given a velocity v to the right. That means these free electrons inside, it's everywhere, they will have a velocity to the right because you are moving the rod. So the free electron inside will have a velocity to the right. And you learned in chapter 19, when a charge is moved in a magnetic field, it will experience a magnetic force. And it is given by this equation. Sign is missing. Why? The angle between V and B is 90 degrees. Sine 90 is 1. Now I am switching to sine now, okay? It's a vector product, not like the flux. Flux is a scalar product, okay? Here the sine. So velocity is this way, magnetic field into the board, that means the angle between them is 90 degrees. Sine 90 is 1. So that's why we don't see the sign. So because perpendicular to each other. So this is the magnetic force. So because of the magnetic force, the electron will end up accumulating here at the bottom. All the electrons will be pushed to the bottom of the rod when it is moving to the right. So that will make, because there is less number of electron at the top, the top will be positive, the bottom will be negative. And the force is this, the magnetic force, it experiences this. But it's not going to happen continuously. At one point, as it coming down, another electron wants to come down, it will experience a repulsion from this electron. The negative charge will push it in the opposite direction. So it will, as it builds up, there will be an electric force in the opposite direction. While there's a magnetic force is down, there will be electric force up. So when this electric force is, let's say it will build up electric field because of the separation of the charges. So another charge wants to come, it will experience an electric force up and magnetic force down. So when the buildup of the electric force is as big as the magnetic force, there will be no more flow, it will stop. So at this point, there will be no more flow of the free electron. It will just, we'll have some amount of positive charge at the top and a negative charge at the top, at the bottom. It will still keep moving, but there will be no more flow of these electrons. It will come to a stop with this charge separation. So this charge separation will result in a potential difference, right? Because we have a positive charge here and a negative charge here. So there will be a potential difference. We can get this potential difference simply by, from the electric field. So Q cancel with Q, the electric field that is created will be velocity multiplied by the magnetic field. And then I can substitute this because potential difference in terms of the electric field, the length of the rod is, the separation between the charges is L. So the potential difference will be electric field into the separation, length L. I can now substitute for the E by this VB, and we get this expression for the potential difference that is generated. Let me repeat what I said. Okay, the final end result, when you have a conducting rod, if you move it perpendicular to an electromagnetic field with the velocity v, then you will end up with the charge separation. That will mean there is a potential difference between the top end and the bottom end, and that potential difference is given by this expression, where v is the magnetic field, which is perpendicular to the velocity, and L is the length of the conductor. Right? So this potential difference is maintained as long as there is a motion through the field of that conductor. And what do you think will happen if I reverse the motion instead of this way, that way? Electron will be going up. So top end will be negative and the bottom end will be positive. So the polarity of the EMF will also reverse. So now we can make use of this. What I will do now, I will take this rod, but I will keep it on a metallic rail like this. It's a closed circuit now. So I will move it to, say, the right side. What happened? This will be positive, this will be negative, but this time they don't have to stay there. You will have a current that flows through this circuit in this direction. The positive will, electron will just keep moving, that means current will be in the opposite direction. So we have motional EMF, right? You can think of it in a different way. What happens now is, this is the loop. When you move this, what is happening to the size of the loop? Now the size of the loop is this much. When you move it to the left, the size of the loop becomes increasing. So the flux is changing through the loop, not by increasing B, not by changing the theta, but by changing the area. So it's a motional EMF. We get the motion. Now we are putting the foundation for the generator, but it will come in the next section. So here you understand how we get the EMF by moving the rod on a closed path. So we can, get the equation again from the Faraday's law. So the EMF that we get because of the change in the flux. So flux is BA, and again, cosine theta is not coming. Now it is cosine theta, not sine theta. Okay, cosine theta is not coming because theta is equal to 0. 0 is equal to cosine 0 is equal to 1. Okay, BA. So A, this should be delta x. Now let's say we move this displacement of delta x in a time of delta t. So you move it by a certain distance delta x in a time of delta t. So the area from here, it has increased to this. So delta A will be this. This much, this part is the delta A. So for delta, yeah, so x, fine. Okay, the B, for the area you put L into x because L is this and this is the x, is actually delta x, not delta x. So L is not changing, only the delta x is changing. So I can take it out. So it becomes delta x over delta t. For delta x over delta t, I can put the velocity. By definition, that is the velocity. So we get the same expression. So even without any of this closed path, it will have a potential difference that is maintained. But when it is have a closed circuit, you will have an EMF that will drive the current in that closed path. So if you want the current, you can divide by the resistance in the circuit, you get the current from this. Okay, I will finish. That finishes actually the section 3 from we covered from section 1 to section 3. So I will not continue to the next sections because that is not for the midterm 3. Okay, midterm 3 from chapter 20 only, section 1 to section 3. What's a generator? So it's the reverse of electric motor, right? Electric motor, we give current, then that guy start rotating. We have a motor. Now we get the reverse. It's also an invention of Faraday, Michael Faraday. AC generator, DC generator, this is all his invention. What naturally comes is the AC generator. That means the current that comes out from rotating a coil in a magnetic field. Naturally, we will get an AC current. Okay, it's not a steady current. It goes up and down, decrease magnitude, change direction. It's an AC current. So that's why it's called AC generator, alternating current generator. Converts mechanical energy to electrical energy. It consists of a wire, a loop of wire which is rotated in by some means, like you can manually rotate it, or falling water, or from burning coal and steam turbine. So there are many ways of doing it. There are a variety of sources that can supply the energy to rotate the loop. This may include freely falling water, heat by burning coal to produce steam. That steam can turn. Yeah.
I want to also ask you, speaking of generators,
Yeah.
Do you know the waterfall? Like
yes. Yeah, turbine. Yeah, of course. Yeah, because the source is all you need is there's a coil. The coil has to be rotated by someone. Who is rotating is the question. When the water is rotating, the falling water turns the turbine. So we get it's a generator. Who is generating that? The falling water. So, or you can yourself manually, you can hire 1,000 people to rotate the turbine. Okay, so it's or you can steam, coal, fuel. Anything can be used to heat the water. Steam. The steam can turn the water. So the fuel source is the coal or the petrol or whatever gas. So it can be anything. Good. So this is the how AC generator work. When you look at it, it looks exactly like what you have in a motor, right? Electric motor. So you have the magnet and you have a coil. So in the electric motor, you send the current through the coil, then the coil start rotating. Now it's the opposite. You have the coil and you have the magnetic field. You rotate the coil. It is not going to rotate on its own. Because you rotate the coil by some means, then you will get a current coming out of the coil. So without battery, so that is the opposite process, AC generator. So I will open this link to show you, the three-dimensional animation. So here, you see there is two rings, not just one ring, two, they are called slip rings. So that coil is there, kept between the poles of a magnet. So there's a magnetic field that goes from north to south, and someone has to rotate the coil. When it rotates, it also rotates with the slip rings, the two rings, and the current will be an alternating current. Okay, so it will be, when it is like vertical, there will be zero current. So when you rotate, what happened? The flux through the coil changes. Then Faraday law comes in. When the flux changes, it doesn't like it, it will induce its own current. That's what I want. So there will be a current that comes out of the coil. So the way, that the current is generated is not a constant magnitude. When it is vertical, it's zero current. As it turns, there will be some current. It will increase in magnitude, then come to maximum value when it is flat, when it is lying parallel to the magnetic field. Then it will decrease, then change direction, and so on. So, without going into the detail, now I just want you to see, what's going on. Let me move a little faster there. So you can look at this, the galvanometer, the current through it's measured by that galvanometer. You can see it is going back and forth. It will be zero, then go one side, increase, come to maximum. Then as it is turning, the current increases. Then it is flat, it comes to the maximum current. Then as goes on, the current will reduce. See, reduce and come back to zero as whenever again vertical. Then as it move on, it will go to the other side. So it's an alternating current. Alternating means alternates its direction as well. It changes in magnitude as well as alternate in direction. So that's why I call AC generator. So so let us go back to this. So this is how it will look like. The EMF from the coil. So you can either plot the current or the EMF. It will look like this. Okay, it will change in value, come to a maximum, come down, then switch direction, and so on. So we call it AC generator. And this is the equation of the AC generator. The EMF E that is produced by this AC generator is given by this equation, where N is the number of turns you have. More number of turns, the EMF will be greater. B is the magnetic field that we apply from the magnet. A is the area of the loop. Omega is how fast the coil is rotating, the angular speed, how many radians per second or how many revolutions per minute, whatever the unit be. And it is equal to the angular displacement divided by time. So you can also, from that, you can write theta is equal to omega t. The theta, which appears here. What is this theta? You should know what exactly this theta means. Theta is the angle between the perpendicular to the coil and the magnetic field. So when it is exactly vertical, perpendicular to the coil, and the magnetic field is the same direction. Theta is equal to 0, right? When it's perpendicular, there'll be 0 EMF. So that is when it is the sine. Theta equal to, yeah. Theta is the angle by definition. What is theta? The angle between the perpendicular to the loop and the magnetic field. So when it's vertical, theta is equal to 0. So no current at that moment. So as it go down, there will be an increasing current. And when it is parallel, that means perpendicular is 90 degrees to the magnetic field, we have the maximum current. So theta can be substituted in terms of the angular velocity of the coil and the time. Okay, so you can be in theta equal to 0, you can start the time to be 0, then this equation will give you the EMF. You can see it's a sine curve, right? Sine curve is something like this only. You have learned your math, right? Sine curve, sine theta versus theta is something like that. Okay, so E is maximum when theta is equal to 90 and is 0 when theta is equal to 0. So theta, you should know what theta means. Theta is the angle between the perpendicular to the plane and the magnetic field. So we have a very nice straightforward question here. Applying the generator equation. Please put your phone away and pay attention here. So here we jump simple question. There is a loop. Mean one loop. N is equal to 1. So he's asking for the EMF that comes from a loop which turns in a uniform magnetic field. The magnetic field is given and the area is given and the omega is given, area is given, and he is asking A, when theta is equal to pi by 2, when it is flat, parallel to the magnetic field, the perpendicular is perpendicular to the magnetic field. Yeah, sine 90 is 1. You will get the maximum value for the EMF. B, and when it is equal to 0, it is 0, sine 0 is 0. Right. So fine. So that is AC generator. It gives, there is two rings, right? They call slip rings. We need two rings to get the current out. And unfortunately, it will be AC, but not unfortunate. AC currents are useful, sometimes more useful than the DC current, because we can transmit over long distance without much loss. Huge amount, high voltage, and it's easier to transport or transmit from one location to another compared to the DC. Right. And now DC generator. So we want sometimes DC, right? We want the steady current, Then what do? We do a small change. Instead of two slip rings, we use one split ring. Split means broken into two, split ring. So when we do that, every time the current direction changes, every half the cycle, the brush touches the other split ring. So every time the current direction changes, also this will also make the direction changes. The result will be the current through the external circuit will be in the same direction. So what you get out through the bulb, in the external circuit, the current will be flowing always in the same direction. So this is how we get the DC generator. A small change in the structure. You make the two slip rings into one split ring. That is called the commutator. And you can again look at it, looking at this animation. So you can click on it. I'm not going to do it now. So this is how it will look like. So instead of the current changing direction, it will be in the same direction in the external circuit because of this commutator arrangement, right? So the current will be, the EMF will be always in the same direction in the external circuit. But still, you're not happy with that. When you say DC, it must be the same value, not something going up and down, up and down. So how do you solve that problem? You will have these commutators, many, not just one commutator. So one commutator like this, another commutator in another direction. We will have around this, you will have in a circular pattern, many commutators. So each commutator will produce, because there'll be a difference between when they are getting 0. So the second commutator will be like this. And there'll be third commutator, it will be little away like this. And so on. We will have numerous commutators around it. So each commutator will have slightly different offset from the previous one. So the end result will be, you will have almost a steady
EMF, a constant value EMF. So that's how you design a DC generator. So to produce a steady current, many loops and commutators, number of loops will be also high, and many commutators at different angle, that will end up in almost steady current. Then there'll be other techniques to make it even flatter, but we will not go into the details there. Right. So we just finished one section about the AC generator. Now we talk about motors again. We did that before. This is not something new. In previous chapter, we learned about electric motors. Now, what is a motor is the reverse of AC generator, right? A motor is a generator run in a reverse. Motors are devices that convert the electrical energy to mechanical energy. So the motor can perform useful mechanical work. So you connect the motor to a shaft, then it will rotate something like So you have motors in for example, your dry cleaner, washing machine, everything has a motor that turns, right? So the principle is just this: the DC motor or the AC or DC motor. Right. Now let us look at these motors in a different angle. Imagine you have a motor, and as the coil in the motor rotates, what happens? So imagine this is the coil, okay? So you connect it to a battery, motor you connect to the battery, right? You provide the electricity, and it will going to rotate to get mechanical energy. So this guy, imagine, is rotating. What happened? When the current flows, there will be magnetic field, right? Now, its own magnetic field will be going through this coil, and as the coil rotates, the loop is kept in a magnetic field, not its own. The loop is kept in a magnetic field. As the coil rotates, the flux through the coil will change. Faraday's law come into action. You don't want that to happen, right? So it will produce an EMF which will oppose this change. So it is like another battery trying to send the current in the opposite direction. So yeah, let's say we don't have this induced EMF from because the coil is rotating. Coil is rotating means the flux through the coil is changing. If the flux through the coil is changing, there'll be a induced EMF which will try to oppose this change. So it is like, suppose you have a battery of 120 volt connected to this motor to make it rotate. This EMF, we call it the back EMF, produced because of the change in the flux. Let's say it is 70 volt. If it is not there, the current through the coil will be 120 divided by 10, Ohm's law. Voltage divided by the resistance will give you the current. But now, because of the back EMF, the effective EMF will be 120 minus 70. So now the current will be smaller. Because of this back EMF, the current will be reduced.
120 minus
7, it will be 50. Sorry. Yeah, I wrote it the other way around. So instead of having a voltage of 120, now we have only a voltage of 50 because of the back EMF is reducing its voltage. So that will result in a smaller current through this coil. So this back EMF is used for EMF that tend to reduce the applied current. The applied current will be reduced because of this back EMF. Yeah.
The current before is much bigger than the.
Yes. When the motor is initially turned on, there is no back EMF, right? Then there will be a big current at the beginning when you start the engine, start the motor. The current is very large because it's only limited by the resistance of the coil when you start. And as the coil begins to rotate, there will be induced back EMF that opposing this applied voltage, and the current will be reduced. If the motor is connected to very heavy load, heavy mechanical load, the motor will slows down because it is going to rotate something very heavy. So the motor will be slowed down because if the load is heavy. which happen, which will decrease the back EMF. If the rotational speed is smaller, the flux change is smaller, it will reduce the back EMF. This will increase the current in the coil. So this is why the power requirement for starting a motor, because at the beginning when you start there will be a big current, so the power requirement is more. When you start the engine, we need a power requirement. And also under heavy loads, also the power requirement is more. When heavy load means it rotates slowly, that means back EMF is less, so the current will be greater. So again, the power requirement is more compared to an average load. Okay, so that is, we discussed the motor again, which is the effect of the back EMF. Now we come to a new section, self-inductance. Right. What we mean by self-inductance, imagine you have a circuit, a simple circuit, a battery is connected to a resistance. Okay, a simple circuit with a switch. So when you close the switch, let's say this is a 10 volt, and let's say this is 2 ohms. What do you expect the current to be? Ohm's law. 10 divided by 2. You expect it to be 5 amperes, right? So Ohm's law, simple Ohm's law, because the potential difference across the resistance is the same as the voltage from the battery, which is 10 volt, divided by the resistance. So it will be 5 amperes. You expect the current in the circuit to be 5 amperes. But strangely, when you close the switch, and if I look at the current as a function of time, you expect it to be E divided by R, which is 10 divided by 2. You expect it to be 5 amp. It doesn't become 5 amp at once. It will gradually build up and come to 5 amp. It takes some time. From the moment you close the switch, for the current to become the final value of 5 amps, it doesn't happen instantaneously. It takes some time to reach there. Why? Can anyone answer why? Again, the Faraday's law comes in. You can imagine there is something called self-inductance. So when the current is turned on, you expect it to be 5 amperes, but the 5 ampere currents, when it flows, it will create, any current will produce magnetic field. Okay, the current that is coming out, it will produce magnetic field. So before, you can think it like a coil, it's a loop, right? A current loop. So before there was zero magnetic field through this coil. Now when you close the switch, because of the current, there will be a self-induced magnetic field. Self-induced EMF, which will oppose this change. You have a current going through that will create a magnetic field, so the flux has changed. Through this coil, okay, this circuit, the flux has changed. There was a zero flux initially, no magnetic field. When the current flows, there will be a magnetic field due to this current. So the flux is changing. What happens when the flux changes? There will be induced EMF, which Faraday's law. Whenever the flux changes, it will resist that change. So there will be induced EMF. We call it self-inductance, because in the same circuit, because of its own current, of the circuit, we will have the change in the flux. Therefore, it will oppose this change, and it will in turn will create a EMF, which will, an induced EMF, which will try to stop this current. Okay, so we don't want the change, right? So it will cancel this current. So, but it will gradually build up. So what happens initially, it will be zero current. Then it will only come to the final value gradually, taking some time. So the time we are talking about is not minutes or so. It is very small, in microsecond or millisecond, fraction of a second. It takes some time for the current to reach that value. So this has some comparison, similar situation with the RC circuit. Okay, when you close the switch in a capacitor circuit, the charge on the capacitor does not come to its final value at once. It will take some time to reach the full charge. Similarly, here we have this inductance, self-inductance, which will delay the current to reach its final value because of this self-inductance in the circuit. This is more pronounced with when you have a circuit with a coil, like a solenoid here, right? You know this. Not one loop, many loops. We call it as a element in a circuit as an inductor. Okay, so this is, you heard this word before as a solenoid, right? Now here in as a circuit element, we call it inductor. So we have learned about resistor, right? You know what a capacitor is. Now the third common element that we will be using, inductor, is just a coil. No, that is as a, not as an inductor, like we didn't give the name inductor to that. That we have the coil for, when you learn solenoid, when a current flows through a coil, it's an electromagnet. So in that context, not as an inductor. So this is something new that we are learning. Okay, we didn't know about this before. Up to section 3, we didn't touch that. Now only we are talking about this. I'm sorry? Yeah, because you are looking, I have added a slide, okay? Because I realized there is some abrupt thing, okay? I jumped from the circuit to the equation without introducing this inductor. So please open the new slide. I just explained just a circuit without any coil in it. Now the effect of inductance, self-inductance, is more pronounced when you have a coil like this, which we call an inductor. Let me explain that. Let's say there is such a coil, which we call an inductor, and the current is flowing. Let's say it's a steady current. Current is flowing through this coil. Let's say it's a steady current. Let's say 10 amperes. It is always 10 amperes. Do you think any self-inductance now? If the current is not changing, is the flux changing? No. If the flux is not changing, will there be an induced EMF? No. Only when the flux is changing, there will be an induced EMF. So case A, nothing happens, no inductance. Case B, let's say this current is changing, not because of your switch on, switch off. Let's say we have this current changing its value. Increase. Let's say if the current may be, say, 10 amperes, it becomes 12 amperes, become 13 amperes. With time, it is increasing. Now, the flux through the coil is changing. The flux through the coil is changing. The Faraday law will come into action. It doesn't like any magnetic flux change. So it will create an EMF which will oppose this change. Lenz's law. So suppose this connected to a battery which is driving the current this way. So the current is flowing like that. There will be an induced EMF which will try to send the current in the opposite direction. Therefore, stop the change. You are increasing the current, therefore you are increasing the flux. I will cancel that change by sending a current in the opposite direction. Right. The change can happen not only increasing, you can sometimes make the change by decreasing the current. So the current is flowing like that, let's say 10 amperes, then after some time it becomes 8 amperes. Again, you don't like it. So what he will do, this is connected to a battery like this, right? The current is sent this way. There will be induced EMF in the same direction as the current. because you reduce, right, from 10 to 8 amperes. So he will put the extra 2 amperes that is lost by having an induced EMF in the same direction as the external battery. So the two cases here, no induced EMF because the current is not changing. These two, the current is changing. One, it is increasing, the other one is decreasing. A current in the coil creates a magnetic field. If the current changes, the magnetic field changes. The changing field induces an EMF in the coil itself. The induced EMF always opposes the change in the current. Right. So the self-induced EMF must be proportional to the rate of change of current. Why do I say that? Because you know from Faraday's law, it is proportional to the rate of change of the flux. That's what you already know. But the flux depends on the current. More current means more flux. Less current means less current. Therefore, I can also say the E must be proportional to the rate of change of current. And I take this equation, then I introduce the proportionality constant. The induced EMF is proportional to the rate of change of current. And the proportionality constant, I am going to call it L, the letter L, and it is called the inductance of the device, which is the coil here. So this inductor has something called a property called inductance of that inductor. And the symbol we use for the inductance of the coil or the device is called is L, the capital letter L. It is like resistor, yeah.
When we put the number in,
Yeah.
the number is negative.
No. Oh, I'll explain the negative. No, L is always a magnitude. L is a magnitude. L itself is a magnitude. It is not never negative. It is always positive. Why do you have the negative sign? Yeah, because the EMF will be such that it will oppose the change. If the current is increasing, it will produce the EMF to decrease the current. If I is decreasing, it will produce the EMF to increase the current. That's the meaning of the negative sign. It will always oppose the change. So this is the inductance of the device. The device happens to be a coil, okay, simple. So we call it inductor. The negative sign indicates that a changing current induces EMF in opposition to the change. So we can say the inductance, I have bolded it, is a measure of how strongly a circuit opposes the changes in the current. How strongly it opposes the change. Not about opposing the current. Opposing the current itself would reduce the current, that is resistance. Okay? So resistance is something that opposes the amount of current. But inductance is something that is opposed the change in the current. So you should not confuse them. Resistance and inductance are not the same thing. So what about the unit? So since I define the E this way, so L will be voltage divided by current, no, voltage multiplied by time divided by current. So the inductance, SI unit for inductance is volt second divided by ampere. That is the unit for inductance, volt second per ampere. But again, you have one name for that, Henry, H. The letter is H, and you say Henry. It's a name. The scientists who work on inductance, Henry. Like Farad is for capacitance, Henry is for inductance. Okay, now I can combine the Faraday's law with the definition of inductance, these two equations. That means this is equal to this. So I get this. And delta T goes away. So you get L equal to, by moving things around, delta t cancel with delta t. So L is equal to N delta phi divided by delta I. So get rid of the delta, you can just put it like this. The L in as this. L of a coil, an inductor, is depend on the number of turns and the flux, magnetic flux through the coil, divided by the current that is flowing through the coil. Right. So let me summarize inductor in a circuit. We can take an inductor coil and put it in a circuit. So it's another circuit element like resistance, resistance, the symbol is this. Resistor is this. And capacitor is this. The capacitance of the capacitor is given by letter C, capacitance. And inductor is a coil like this, like a spring. So these are the basic elements of an electronic circuit: resistor, capacitor, and inductor. Resistor will oppose the current, try to reduce the current. Capacitor will store charge, and inductor will oppose the change in the current. Okay. So inductance can be interpreted as a measure of opposition to the rate of change in the current. Remember, resistance is not opposing the change in the current, it just opposes the current. It tries to reduce the amount of current, that is a resistance. As a circuit is completed, the current begins to increase. Okay, when you close the switch in a circuit with an inductor, the current will not reach its final value at once because of the inductor. It will come to the final value only gradually. It will not be instantaneous. So let's look at our first RL circuit. Remember, we had our C circuit. That is, the moment we learned about the capacitor, we created a simple circuit with a battery and a resistor and a capacitor. Now, we create a simple circuit with a resistor and an inductor. So this is the resistor, this is the symbol for an inductor, a coil. And the resistor has a resistance R, the inductor has an inductance L. So you connect the circuit and close the switch. Inductor has no resistance, ideal inductor. The coil, the wire has no resistance at all. It is zero resistance, it only has inductance. It will not just oppose the current, it will only oppose any change in the current. If the current is steady, nothing happens, it is happy. Okay, so the resistance, there will be nothing impeding the current. But the moment the current changes, then it will produce a current in the opposite to this change, thereby the increasing or decreasing the current. So that is how an inductor works. You saw before this graph that finally the current has to reach this value E over R, the final current, but it will not come to that value at once. It will take some time to reach that current. So we say time constant, and the symbol is tau. We came across this before also with the capacitor. There was a time constant for capacitor RC circuit. Now we also have a time constant for RL circuit. Okay, there are two different things. That is the time constant for RC circuit, and this is the time constant for RL circuit. But the definition is similar. It is the time required for the current in the circuit to reach 63.2% of the final value. For the capacitor, it is not the current. it is the amount of charge. It is the time the RC circuit takes to reach 63.2% of the maximum fully saturated charge value. Here, it is the current value, the final maximum current value. So the equation, this is the graph, okay? So you don't get the current final value at once, it will take some time. The time when it reaches 0.632 of the final value, at that time is called the time constant. The symbol is again tau, same as the RC, the capacitor time constant. But the value is L over R. Anyone remember the time constant for RC circuit? No. The formula for the time constant, RC. Yeah. This is the time constant in RC circuit is simply RC. But the time constant in RL circuit is L over R. So the equation is similar. So what you had for the RC circuit is the Q at any time t is the maximum Q 1 minus e to the power t divided by tau. Tau is RC. This is the time constant for RC circuit. And for the RL circuit, is not the charge, it is the current. This is the maximum current. 1 minus E T divided by tau, but the tau is now L over R, not RC. So that's the only difference. So you can show that, when the time is equal to L over R or the time is equal to tau. So you put L over R for the time. So here I will substitute L over R. L over R cancel with L over R. So it become e to the power minus 1. And if you calculate this, it is exactly 0.632. So our definition. What is the tau in LR circuit? The time for the current to reach 63.2% of the final value of the current. Okay. So the current at any time t, so this is the equation we will be using for a LR circuit is given by this equation. For the E over R can be written like this. So when it is written like that, you should know I max, you should replace it by E over R is the EMF of the battery and R is the resistance in the circuit. Okay, this is the final slide in this chapter, chapter 20. Okay, so then I will stop and we'll take the attendance. So what is this? It is similar to what the chapter on capacitance. We've ended it with the energy stored in the capacitor. In a capacitor, energy is stored as an electric field by the charges. When the charges are separated, there's electric field in the capacitor. So the energy is stored as in an electric field. Okay. Now here, when you have an inductor in an RL circuit, the energy is stored as in the magnetic field that is in the inductor. Okay. When the current flows, there's a magnetic field. So the EMF induced by inductor prevents the battery from establishing an instantaneous current. So the battery has to do work against this resistance, right? So the battery will drive the current through this. So it will establish this magnetic field inside. So the battery has to do work to produce this current, and the energy that is stored is given by this equation. When a current through the coil is I, and the inductance of the coil is L, the energy stored will be given by this equation. Again, you don't need to worry about how we get it. We just have the equation.